Okay, so this is Lab 2 um, for Physics 2211 by Yuchen. So in this lab, we'll drop an object from rest and observe its motion. We want to test for the drag force, whose direction is opposite to the direction of the object's motion. In this lab, we will be covering topics such as Newton's second law, gravitational force, and drag force. Here are some formulas of interest. We have the velocity update formula, position update formula, um, force of gravity, and drag force. So in this lab, we have three models. One from Tracker, one computational model with drag, and one without drag. Here is the computational model without drag. So in this computational model, the code, change the mass to match the mass of the demonstration that I did, which in my case was an AirPod case, which was 0.058 kilograms. My delta T, I adjusted it to match the one tracker. And since this is without drag, the drag thingy is 0. Here, I adjusted the force to match the formula for gravitational force and changed the velocity update formula accordingly. Here is the computational model with drag. Everything is pretty much the same, except this time we have the force of drag, and it's just plug in the force for drag, the formula for drag, and we add that to the force of gravity. So I know I'm supposed to have a slide for tracker, but I accidentally deleted it. And I don't feel like doing it again. So you can just trust that it is an AirPod case dropped from my desk at a height of 1 meters. So here is the data for all three models. The green one is the computational model with drag, blue one is tracker, and the orange one is the computational model without drag. And as you can see, obviously the one without drag drops the furthest. The computational model without drag drops the least far, and the one with tracker somewhere in the middle. So what if and conclusion? In the models with drag included, a terminal velocity is predicted. This is because the drag force, which increases with the square of the object's speed, eventually balances the force of gravity, resulting in a net force of 0. This means that the object stops accelerating and reaches a constant velocity when the forces are in equilibrium. In contrast, the models without drag does not predict a terminal velocity. In this case, the object continues to accelerate under the influence of gravity without any opposing force to balance it. Therefore, the velocity versus time graph for this model shows continuous acceleration without leveling off. When the object is initially thrown downward instead of being dropped from rest, the terminal velocity would be different from the case when the object is initially dropped from rest. This is because the initial velocity of the object affects how quickly it reaches terminal velocity. In a case where the object is thrown downward, it already has an initial velocity in the direction of motion, which may be greater or less than the terminal velocity. Consequently, the object will either accelerate or decelerate until it reaches terminal velocity, but the specific terminal velocity achieved will depend on the magnitude of the initial velocity. Using the computer model to examine the object's velocity as a function of time in the case where the object is thrown downward initially will show a different velocity versus time behavior compared to the case where the object is initially dropped at rest. In this scenario, the object's velocity may exhibit oscillatory behavior before eventually stabilizing at the terminal velocity, which would be different from the terminal velocity achieved when the object is dropped from rest. And that is my lab. Thank you for listening, and if you give me a good grade, I'll give you a good grade.